All right, we are going to look at sequences and using the sequence test to determine if they're arithmetic or geometric. So we're going to have one of three options. The sequence is going to be arithmetic, it's going to be geometric, or it's going to be neither. And so it could be some other sequence. So I have two sequences here, and we're going to use these tests and determine arithmetic or geometric. So the first sequence, I'm taking the second term and subtracting the first term and looking at some value. And if that is the same value that I add to each term to create the next term in the sequence, then I found an arithmetic sequence. If I take the second term and divide it by the first term, and I find that term is multiplied by each term to get the next successive number in the sequence, I found a geometric sequence. If neither of these conditions are true, then I have something else, and so I can't use the general forms for arithmetic or geometric to generate these sequences. So the first thing that I have here, I have my second term is 5, and I'm going to subtract 2 from it, and that's going to give me 3. The second term divided by 2 is going to give me 2.5. So when I look at going from 5 to 8, if I add 3 to it, I do get 8. If I multiply by 2.5, I'm not getting 8. So this one doesn't work. This one does. So let's continue on. 8 plus 3 is 11. So it seems to be that we have an arithmetic sequence. So we're going to use the general form for the arithmetic sequence to write this as a sequence in a kind of a recursive type form, and then we are going to switch that to a function. So a sub n is going to be equal to a sub 1 plus d times n minus 1. That's our general form. And so our first term is 2 in this case. The d value is what we just calculated here. That was the 3. And n is going to be the term in the sequence. And this is a sub n. So now we can simplify this. We can multiply 3 times n and 3 times negative 1 using distribution. So I have 2 plus 3n minus 3. And I'm going to simplify where I can. And so at this point, I have a sub n equals 3n minus 1. You may notice that this is the slope-intercept form of a linear equation. So we're just going to make use of that form and rewrite this as a function. A sub n is going to be replaced by f of x. 3 is going to stay the same. N is going to be replaced by x, and then we're going to leave the negative 1. So f of x equals 3x minus 1 is a function that will generate this sequence starting with 1 as your input and progressively getting larger with the natural numbers. It will generate this sequence. So you can find any term in the sequence by putting the number of the term into this function that you want and generate that number. So let's do the same thing with the second sequence. We're going to go through the test, determine if we have arithmetic or geometric, and then create a function which will generate the sequence. And so I have 6 minus 2 is going to give me 4, and then I have 6 divided by 2 is going to give me 3. So looking at 6, if I add 4 to it, that's 10. That doesn't give me the 18. If I take 6 times 3, that does give me 18. So this one failed in this case. And so now I want to look at 3 times 18. Does that give me 54? I believe that's going to work. And so we are looking at the geometric sequence this time. So we want the general form for a geometric sequence. And this is the general form. So we have the first term times the common ratio, and it has an exponent of n minus 1. So we're going to replace those values. Again, I started with 2, and the common ratio I just calculated, that was the 3. And this is to the n minus 1 power. and this is a to the n. We look through, is there anything to simplify? There is not, and so now I'm going to rewrite this in function form. And so I've already used f of x here, so I'm going to use g of x down here. I'm replacing a sub n with g of x. Keeping the 2, keeping the multiplication, keeping the 3. The n is going to be switched to an x. And so I have this function is my function that will generate this sequence. We are going to look at recursive sequence equations, and we are going to start with this second order homogeneous recursion equation. I have a sub n equals 2 a sub n minus 1 plus 3 times a sub n minus 2 for any integer that is greater than or equal to 2, and our initial conditions are going to be a sub 1 is equal to 1 and a sub 2 is equal to 3. I have a characteristic equation here. This happens in these situations. It turns out to be a quadratic. So we're going to need to use some ideas about quadratics in here. And then this pattern is going to hold. Notice this pattern is established with the sequence being a sub 0. So we are going to have to establish what a sub 0 is. And I also want to establish what a sub 3 is so that we can check that our sequence or our function at the end is going to generate the proper sequence. So the first thing that I want to do is I want to go through the steps in how to generate the next term in the sequence, and then I want to look at going in reverse and generating the a sub 0 term. So the first thing I want to do is I want to generate the third term, a sub 3. So I want a sub 3. If I replace n here with 3, I have to replace 3 here for each of these n's as well. And then I want to simplify. So I have a sub 2 here and a sub 1 here. Those were my givens. Those were my initial conditions. So I'm going to plug those in here. And then I'm going to simplify this. So I have 6 plus 3 is 9. So my third term is going to be 9. Now I want to look at how to find this a sub 0 term because I need it for this pattern to hold with our characteristic equation. So looking at what I have here in this line, I want to construct a way to get a sub 0. So notice I started with a sub 3 and I had 2 and 1 here. So I want a sub 0 here. So over here, I need progressively smaller terms as well. But that's not going to work. That's going to generate, this would be negative 1. And this is going to be negative 2. And that's well outside of our reach here. So this approach isn't quite going to work. But if I start with a sub 0 on this end and then add 1 each time, that strategy is going to work a little better. So if I start with 3 times a sub 0 and then go 2 times a sub 1, I will have 2 times a sub 2 here. I know a sub 2, I know a sub 1. I have those as givens. 2 and 3 are just scalars. And so the a sub 0 will be the only thing that I don't know. So I can solve this problem and find a sub 0 this way. So this is the strategy that I'm going to use. So substituting in, I have 3 equals 2 times 1 plus 3 a sub 0. And I'm going to solve for this a sub 0. So I'm going to subtract 2 from both sides here, giving me 1 equals 3a sub 0, divide both sides, and so I have 1/3 equals a sub 0. So now I'm going to use this characteristic equation and rewrite this. So I need to move a sub n over to this side so that it's equal to 0. So I will have negative a sub n plus 2a sub n minus 1 plus 3a sub n minus 2 equals 0. And then I want this lead to be positive. And so I'm going to multiply through by negative 1. So I have positive a sub n minus 2 a sub n minus 1 minus 3 a sub n minus 2 equals 0. And that matches my characteristic equation here. I have a negative here, a negative here, negative here, negative here. This is my a value and my b value. And so I'm going to rewrite this as this quadratic. So this is h squared minus 2h minus 3 equals 0. So I'm substituting the characteristic form in here, and now I want to factor this quadratic. So I'm going to have h minus 3h plus 1, and that is going to be equal to 0. And then we're going to use the zero product property here to set each of these equal to 0 and solve for h individually. So h minus 3 equals 0 will give me h is a positive 3. H plus 1 set equal to 0. Solving for h will get h equals negative 1. And we're going to use these terms, and we're plugging them in here. I've already done that. So we have an r and an s term that are these zeros of the function plugged in here, and the exponent is the subscript here. So I have sub 0, sub 1, and so a sub 0 was the 1/3 that we calculated over here. So this is equal to 1/3, and this is a sub 1. That's going to be set equal to 1. And so I want to solve this system equation so I know what C and D are, and I'm going to eventually plug them into this, which is a sub n. So I have a generalized form of this. So I have to work through this. So I'm going to simplify here. So these things to the 0 power are going to generate 1s. So it's going to, the top line is going to be C plus D equals 1/3. The second line I'm going to have 3C, and then I'm going to have a negative D, and that's going to be equal to 1. So I'm solving this system of equations. It's going to be fairly straightforward. If I solve this for D, that's going to give me D is equal to 1/3 minus C, and then I'm going to plug this in down here. So I'm going to have 3C minus 1/3 plus C equal to 1. And when I solve that, I'm going to have 4C equals 1 1/3. And so then I'm going to want to solve for C on this. I'm going to divide both sides by 4. So C is going to equal 4/3 divided by 4. So I'm going to have 1/3 there. So I'm going to plug this in for my general equation now. So a sub n should be equal to C was 1/3 times, I've been using 3 here in the r's place, so I'm going to bring that 3 back in here and put the exponent of n. The second term, though, it's nice. We ended up with, we didn't solve for D. I want to plug this 1/3 in for C here, and we will see that D is equal to 0. So we're ignoring this term. So now we might want to check to make sure this works. So earlier we determined that a sub 3 should be 9. If I plug 3 into this, a sub 3 equals 1/3 times 3 to the 3rd power, which is 9. So this formula does work. So now the last step is I need to rewrite this thing in function form, because ultimately we are looking for a function that does the same thing as this recursive formula. And so I'm just going to replace a sub n by f of x. And then the right-hand side is going to be the same, except for the n is going to be replaced by x. And then that will be our final function that will generate the sequence that starts with a sub 1 and moves forward. So if I put 1 into here, I'll have 3 to the first power divided by 3, and that'll give me 1 back, and so on. And so this is our final function that does the same thing as this recursive equation and generates a sequence. So now we are done.